All right, so welcome back, everybody. I'm going to continue. So where did we leave? So the first thing that we learned how to do is one of the buzzwords of data cubes and OLAP is we slice and dice. So typically what you do is that you put some dimensions here in the slicer zone and you take specific values. You have a slice of the cube and 2 dimensions, also 1 or 3 depending, but 2 dimensions typically you put in the rows and the columns and get displays like this. This is called cross tabulation. Now, there are other things that we can do, of course, because this looked like simple. It's just like a selection on the underlying data. But of course, we can do more fancy things. And this is the reason why there's a few differences with, between cubes and tables. So the next thing that we can do with the cubes is an aggregation. So we had this for tables, but for cubes, it's done in a very specific way. Look at what happens here. What if I want to aggregate over that dimension? It basically means that I'm merging cubes. You see, now I'm merging the cubes in this direction. So in that case, I will have 2 dimensions left here, but the third one is merged. So let's try to do it on the facts table to give you an idea. So imagine that I want to aggregate on the across the location. So it means that I want to add Germany plus Switzerland, assuming these are the only 2 locations of my company. This is the whole world for all practical purposes. So we're aggregating for the whole world, but we need to be careful. 22 goes with 22, 21 goes with 21, Peter with Peter, Mary with Mary, right? So now these are my group. These 2 get aggregated, these 2, these 2, these 2, right? And I'm going to, let me add them. So 1 plus 5, 2 plus 6, and so on. This is what I get. So now I have world domain because I aggregated in here, and I have 22, 21, Peter, Mary. So you see, this is what I have. And this is the sum of this. So that was derived in this way. Who is with me? Okay. This is an aggregation. Technically, there is a fancy name. What we've just done is a roll up. So roll up, and I will get more into the details of roll up, drill down, and so on. But we basically completely rolled up the location dimension. This is what happens. Now we have the whole world, and I lost everything else. I'm just interested in the whole world. Now, again, it looks like slicing now because it's the world everywhere. And typically what you do is you put it in the slicer zone, but now it's the whole world. It's not just a specific geographical location. So I have the whole world, still USD, and I have my dimension. And now I can, again, cross-tabulate it nicely like this. In fact, some of you might already know that you have that in almost any spreadsheet software. Who has already used the pivot table feature of Excel or LibreOffice or any other? Many of you, right? This is the pivot table in spreadsheets. This is where it landed in the end to end consumer products. And it's really nice, and I recommend you do that. I really recommend you do that. The way it works is that you import something like this as a CSV file or something into Excel as some spreadsheets, all the columns and then the value, and then activate in the menu the pivot table. And what you get is an interface that looks just like this, and you can drag and drop things around. So you can drag and drop the domain here, sorry, the period here, the sales should be period here. I thought I fixed it, but anyway. Salesperson, you can drag and drop in there. You can basically just arrange your cross-tabulated view just by moving and dragging and dropping the dimensions, right? So it's something that you don't even need to be a computer scientist to understand. This is really for a general audience that business people can do these sort of things. But what we're interested in here is the model behind this, and we'll see an implementation of SQL of how to prepare the data that goes in the cells over there. All right. So you need to understand that this goes beyond just relational tables. These are really cubes. And SQL is not able to do that. This is the slicing and dicing and organizing in a cross-tabulated view. This is beyond SQL. Okay, so now what we can do, and again, you can do it in any spreadsheet software by just with a few clicks. You can prepare totals here for the whole domain of all salespersons, and then the whole period here in that last column. And you have automatically the totals computed, and this is the grand total, right? That is both the sum here and the sum here. And again, you can do it with any spreadsheet software very easily. So these are also aggregations, but here we aggregate, but we keep the detailed value, right? We show the aggregated data alongside the individual values with fancy lines that say it's a total, okay? Now, the reason we can do that sort of things is that there is a feature that the dimensions in data cubes have, and this is something we don't have in relational tables. It's that the dimensions organized their values in a hierarchy. So in the case of the times, here it was flat, just a flat list of years. The people, it was also a flat list, but the most obvious hierarchy is for the world. You can have the continents, the countries, the cantons, the cities, and so on. It's a whole hierarchy. So now you probably see how it makes sense to have intermediate subtotals, you know, for every time you go up the hierarchy, you can have an intermediate subtotal and then a grand total for the whole world, right? In fact, it's the same for the periods. I didn't show it to you, but in spreadsheet software, it will automatically arrange the date with years and then quarters and then months and so on. So that's also a hierarchy, in fact, in there. So you can have intermediate subtotals for every month, for every quarter, for every year, right? So you see, this goes beyond what relational database systems can actually do. And in fact, so in that case, you probably notice that for the rows, the way I put the total is just with some line that says, you know, just like you do in primary school to express that it's a total. But observe what happened with the columns. With the columns, I have something very particular here with an L shape. You see this cell right there, it's an L shape. So it basically means that you have your members, so the values that the dimensions can have, but they are in the hierarchy below the all times domain. But in order to display it, this all times, we continue it here in such a way that it naturally puts the total there. And with the L shape, we make it very clear that these are the totals of all times, right? Who gets it? The intuition of that? Awesome. And if you generalize it to hierarchies of countries, this is what you get. These beautiful displays like this, that you have like Zurich, Geneva, Interlaken, then here you have Switzerland, and with the L shape, you make it clear. Then you have Germany, intermediate subtotal. Then here you have Europe, again with this L shape, and the whole world like this. So this is how you do it on the columns, right? And for the rows, we don't do L shapes typically on the rows for some reason. Instead, we use indentation in order to make the hierarchy clear, right? So L shapes on the columns and indentation in the rows. So it's kind of funny because technically we have trees in there, right? We do have trees in the dimensions of the data cubes, but these are very specific trees. It's really not like JSON or XML. It's just part of the metadata, the trees in that case. Okay. All right, so this is just to give you an example of a more complex hierarchy on the columns, a more complex hierarchy on the rows, and you can also have both in there. All right, so that's what the sort of things you do with data cubes. Now, remember when I rolled up, when I aggregated over the Switzerland plus Germany, let me do it now with a more complex hierarchy. Imagine that you're sitting in front of your pivot table like that, when you have these fancy buttons plus and minus that allow you to make things disappear. Imagine that you want to forget about the individual cities. It's called rolling up. So I click and then I get this, you see? Then I do it the same. I want to roll up again. Then I forget about the countries, get the continents. And then I roll up here all the way up to the top level, the whole world. And in fact, when I do that, I can again put it up in the sliders. And then I still get a cross-tabulated view. But that time, I only have one dimension on the rows and nothing on the columns, right? So now you have one example where there's only one dimension on the rows, all right? And the opposite of roll up is called drill down. It's when I start like this and I click plus, 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 I just go into the details. So roll up, drill down, right? Okay, so this is what you can do with data cubes. And now probably that answers your question, right? If you're just sticking to SQL, you cannot do that sort of things on the cubes. All right. So now I'm done with the logical part, right? We can slice, dice, roll up, drill down, and so on. So now, how do we implement it? Well, it's very complex, and in fact, it's much more complex than what I can explain to you in 1 week. In fact, it's so complex that, again, an entire sub-industry appeared in the 90s just for that, with a lot of companies in that ecosystem. So I'm going to show you one possible implementation on top of SQL, but now you have to realize that SQL is no longer the logical layer. When we look at relational database, SQL is the logical layer, and then maybe it's C++ or Java, the implementation. Here, SQL is the physical layer. It's the implementation that is done in SQL, but the end user doesn't see the SQL. They're not supposed to see the SQL. So this very implementation that I'm going to present is called rollup, relational rollup. And the alternative is molap. That's an alternate way of doing that. That is more native with in-memory indices and materialized views. So I'm going to focus on rollup. So how does that work? Well, that shouldn't be new to you, right? In the notion of facts table, we can start with that because that's something that SQL can manipulate. So we are going to have a facts table like this with one dimension for every attribute and then the value in the last attribute. Note that it's a very specific relational table, right? I cannot take any relational table and do that. It's a very, very specific kind of relational table that works like this. In fact, there are even ways of characterizing that with higher normal form. It goes all the way to the 6th normal form, in fact. All right. Just as a parenthesis that I'm quickly opening, you might have cases in which you have multiple values. They are called measures. In the context of accounting, which is the way that this is used in business reporting, the measures could be profit and loss, revenues, assets, non-current assets, current assets, property, plant, and equipment, like everything you want to measure. Could be the sales, the number of the quantity sold, the profits, and so on. So in the case that we have multiple measures, we actually get a more complex facts table like this with the dimensions, but then multiple measure columns. However, there is a way, it's like magic, we can actually bring ourselves back to the original problem. The way we do that is that whenever we have multiple measure columns, we can use our magic and transform these columns into members in here. So instead of displaying it like this with 2 columns, I can just do what's called an on-pivot. And now I put it in there as an additional dimension that didn't exist here. And now I'm back to a single value dimension. This is called pivoting. This is called unpivoting. And in fact, SQL was extended with syntax allowing you to pivot and unpivot relational tables. And now most of the relational database management system do have this implemented in SQL. I'm just not showing it to you to not have too much material, but there is SQL syntax to do exactly that. Why am I saying that? I just want to say that I'm not going to talk about that case because we can bring ourselves back to the case where there is a single value. So this is why here I'm going to assume a single value for the purpose of what I'm going to show you. Now, what's going to happen is that we have our facts table, but it is accompanied by a few more tables that we call satellite tables. Every dimension in there has a satellite table, right? That has more information. For example, a dimension might be a customer, and in the satellite table, you will find the address, the phone number, and so on, so other dimensions, right, about the product. For example, you might have a geographical dimension, and then you're going to have the country, continent, and so on in the satellite table. There are people who love normal forms so much that this is not enough of a normal form. They want to be even higher normal form, even more tables. That is called the snowflake schema, because it reminds us a bit of the shape of the snow, right? So this is a snowflake schema. It just means that you have even more satellites around the satellite. It's a whole solar systems with the moons and so on, right? Okay, but this is just higher normalization. Okay, and to give you an example, we have a fact table over there that points via the city dimension to a satellite table. That's the snowflake here. So there's a level 1 with Interlaken is in Switzerland, and then you have Switzerland that is in Europe. From a relational database perspective, it's easy. This is just a foreign key pointing to a primary key, a foreign key pointing to a primary key. That's the typical way you normalize your data in the relational world, and then you join them back to make it make sense together, right? All right, so something that people like to do in some cases, and in fact, especially if you want to work with a spreadsheet software, you can also denormalize that. You can take the facts table together with the satellite table and join everything back in which case you get some expanded facts table with multiple columns for every dimension. For example, for the location, you might originally have had only the city, but by denormalizing and joining back with the satellite tables, you also get the country and the continents. But you need to be careful because they belong together, right? There is a functional dependency here, right? Switzerland is always in Europe and so on. So these three columns are really the same dimension. They are not orthogonal to each other like the product, the salesperson, or the time would be orthogonal. So this is really a denormalized fact table. For whom is that clear? All right. Now, because we have a relational table, I'm going to discuss how we can use SQL as the physical language in order to create the data that we need to populate the cross-tabulated view. Okay? What's very important is that SQL is not going to create the cross-tabulated view. It's not capable of that. It's like, you know, if you have a cat, the cat can eat the food. You cannot ask the cat to cook the food that it's going to eat, right? It's exactly the same thing with SQL. SQL is not capable of creating the cross-tabulated view. The only thing that it can give you is the data you need in the form of a table. And then you need an extra implementation to take these values and put them in the nice fancy cross-tabulated view. There is a language, just for mentioning it, called MDX, for multidimensional expressions, that is capable of creating cross-tabulated views, right? And MDX would be for cubes, specifically for cubes, while SQL is for tables. And you can implement MDX on top of SQL in the sense that SQL will create the data you need. But I'll come back to MDX a bit later. Just one slide on it. I'm not teaching the language. Don't worry about that. All right, so let's imagine for the purpose of what I'm going to show you a sample cube right here with 3 dimensions and a value. So I'm going to have some date, some product, some customer, and then the quantity that the customer bought, all right? So this is a cube. If you look, there are three possible dates. There are 2 different products and 2 different customers. So the cube is a 3 by 2 by 2 cube, right? So 3 times 2 times 2. So 3 times 2 is 6, times 2, 12. And I have 12 values in there, all right? Again, this is the facts table of an actual 3 by 2 by 2 cube. Yes?
How is the hierarchical access structure stored in practice? Is it separate from the data cube?
Oh, I see. So technically, I've showed you it. I've showed it to you here when I did that. When I showed you the satellite tables, this is how you can actually store a hierarchy in SQL. But you really need to be aware that SQL can only do tables. So this is a physical implementation of a hierarchy. It might not be the most optimal one, right? You might find other ways to implement it. So it feels a bit of a hack to implement the hierarchy in this way. But this is just to remind you that SQL here is the physical layer. It's not the upper layer. In MDX, you would have the dimensions hierarchies with points, just like object-oriented language. So you can say Europe.Switzerland.Zurich and so on, right? But SQL is not able to do that. So we need to hit it a little bit with a hammer gently, and then we fit some hierarchies in this way into the tables. Did I answer your question? Yeah, awesome. Okay. Now, in that case, I don't have any hierarchies because I didn't want to bother you with that, right? So I do a simple case with flat dimensions, 3 flat dimensions, and that's it. So these are possible satellite tables, just to give you an example in my very specific case. So I have a satellite table for the dates together with the year and the quarter. Then I have the customers with the country and the phone, and then I have the products with the brand and the price. Okay, so this could be my satellite tables. And what I need to do in order to query my data is, so I could use select from where to get the table, but I could also join it with the satellite table, right? For example, if I want to get the year for the date, I could join it with my satellite table for the time and get that, right? Again, it's just an example. In practice, you could get the year just with a function in the library of SQL that would directly give you the year of the date. It's only for explaining the way you would join with a satellite table, okay? But again, what I'm going to do now to show you the aggregation is I'm going to assume that I have a standalone facts table where I already took the year and the brand and the customer, and that's it. So I'm going to forget the satellite tables and just focus on that one facts table, as a single relational table. And we are going to be working on that one. So what can I do? Well, first I can look at it as a start. So select the year, the brand, the customer, and the quantity, right? From sales. So sales is the name of the table. In order to slice, we've already seen before that it's just a selection. So it's the where clause. All I need to do is where year 2017, and I get this, which is a subset of the original table with 4 values. This is all SQL can do. Then, with additional code in some other language, JavaScript, CSS, or whatever you want, you can take these 4 values and put them as a nice cross-tabulated view and so on. But SQL will not do it for you. This is as far as SQL goes. All right, then I can slice even more on Samsung in this way, and I get these 2 values. Okay, so this is for slicing. Slicing is the easy case, right? So just a where clause. Now, it's interesting to look at the aggregation. How do we do rollups in SQL? So let me start again with my full table with my 12 values in there, organized in 3 dimensions, so 3 times 2 times 2. Now, imagine that I want to do a rollup. I want to roll up on the customer. What that means is that I want to aggregate over the customers, right? So I want to add, for example, I have here 17 Apple Peter. I want to add it with 17 Apple Mary. This is what I mean with rolling up. So I want to compute an aggregate. So this is 1 plus 5 gives me 6, you see, 2017 Apple. So what happened is that I lose that column, right? I know that this is fully aggregated, it's rolled up, and then I have only the other columns left. How do I do it in SQL? Well, it's a group by. I'm going to be using a group by, but now there's something counterintuitive that at first might not make sense, but if you think of it, it does. If you roll up on a dimension, you do that not by putting it in the group by, but by not putting it in the group by. It means that in the group by, you put everything else that you don't roll up, and you omit the one that you are rolling up. So we omit customer from the group by. I keep year and brands. This is why they appear here. And then I put them again in my select clause, and I sum over the quantity, right? Note that you can also use count, mean, max, so there's other aggregation functions. And in spreadsheet software, you can also select that, right? You can also say when you aggregate what you want to, what function do you want to use. So this is a roll up on customer. In order to roll up additionally on the product, again, I need to remove from the group by. Whenever I want to roll up, I remove from the group by. So now I remove the brands, and I get now the aggregation for every year. And now it's for all products and for all sales people. All right. And finally, I can even roll up on the last dimension and get the grand total of everything. That is 34, right? Note that in the original data, this is all computed, right? This was the original data that has the individual values. That's the snapshot you took from the database. And this is computed with SQL, this, and this. Now, imagine, you can drill down. If you want to drill down, for example, differently in year and brand, then you add, right? So rolling up means you remove from the group by. Drilling down means you add back to the group by. Okay? Now, here's the thing. You probably wanted to compute these subtotals and these aggregations because your goal is to put it in a cross-tabulated view of some user. So it might be that for the cross-tabulated view, you need all of that, right? The user both wants to sum over a year and brand and so on in such a way. And they want on the rows, for example, the subtotals for the years, and then on the columns, the subtotals for the brands. And then at the bottom right, the grand total, right? This is inefficient because it took us 4 queries to do that. See, 1, 2, 3, 4. So it's going to take more time than we need. So how about trying to compress that in a single query to get all of that data in a single shot? Well, we actually can with what we know of SQL, right? So first, if I want to merge them, I need a single table, but this is fine. I just add some nulls, right? In order to make all the tables with the same colors. So I can just merge them in this way by putting nulls in here, and then 2 nulls for the grand total, right? So this is one way that we can do that. And on the SQL, if I reason in that way, I just use a union, right? It's select, union, select, union, select, union, select, all right? And I get this. So now this is pretty much the state of things before all of these new companies existed and the business analytics took over in the industry. We could kind of use SQL in that way. But what happened is that when many different people started to use SQL in the same way to implement physically support for data warehouses, the SQL vendors and in fact even the SQL standard was extended to make it a bit easier. So what happened is that this here with the union, it has a specific pattern. Some new syntax was created that looks like this. So you basically still do your 4 group bys, but the way you express it in the syntax is a bit easier. You just say group by grouping sets. And that means you first group by year and brand, then you group by year, then you group by brand, then you group by nothing, and then you take the union of that. And that is called a syntactic sugar, because that's really something for something that already existed, but a bit more compact. So group by grouping sets, now you have all the combinations. So this is the first thing that was added, and that's something new in the syntax. It is in PostgreSQL, by the way, you can actually try it. Now, it's not enough, of course, and we can do it even better with group by cube, which is again a shortcut for the same thing. So when you do group by cube, it's automatically going to take all possible combinations. Mathematically, you're looking at all elements of the power sets of this. So empty set, singleton, and everything. So if I have n, so here it's just 2, but you can have in general 3, 4, or n dimensions in here. What is the number of grouping key combinations that I'm going to get if I have n dimensions here? Yes? 2 to the power of n, exactly. And here 2 to the power of 2 is 4, 3 would be 8, and so on. Exactly. So that's the power set, right? That's the thing to remember. So group by cube does exactly that, and it exists in PostgreSQL. You can actually write that and get this. This is how important data cubes were, so that it was added to the language. Okay, and then you take this, and with additional software, because again, SQL is not able to do that, so you need additional software, you can put now this into this cross-tabulated view. All right, and then the user will continue to drag and drop things or select a different filter and so on. But you can imagine how in the background, the SQL query is just modified to deliver the data that you need. All right? Okay. Now, what about hierarchies? Because so far it was flat. What if the dimensions are not flat and I have hierarchies like that? How do I do this? How do I prepare a view like that? So technically, you could view it as some sort of aggregation happening like this, where you first have all the cities, then you aggregate, you only have the countries, then you aggregate again, you have only the continents, and you get something like this. It's the same idea of getting some nulls, but the pattern is different. Because here, it's a roll-up pattern. It means that there is a wave from the right to the left here, right? It goes like this. It's not like what we had before, where if you look here, there was nulls here, nulls there, so that was more symmetric. Here, there is really some hierarchy that you see here, right? So city in a country, in a continent. So this is what you typically get here. So what if you want to retrieve the data for a view like this? Well, technically, it's the same thing. You just use group by, group by, group by, right? So maybe if you want, let's say, by years and quarters, that's the example here. So you want the subtotals by year and the data per quarter and the aggregated data over all times. Then all you need to do is group by for every quarter and year, then group by for only every year. Then you have the aggregated data per year, and then no group by at all. You just roll up everywhere and you have a single grand total. So again, you can create the tables like this. You can union creating nulls in the process like this, and you get, again, the data ready to be put in the cross-tabulated view. Again, you can use group by grouping sets to obtain this, but now you see the different pattern. Now there is some more linear pattern in there. And there is also a shortcut for that. It's not going to be group by cubes. Group by cube is going to be group by roll-up, right? Year, quarter, and that actually does that. Bonus question, if there's n dimensions here, how many grouping keys combinations will I get with group by rollup? Almost. See, n is 2 here, but it's 3, right? Almost. Almost the other way. N plus 1, right? Because of the empty one. So it's n, you see here, year quarter. You have year quarter, you have year, n's the empty one. So n plus 1. Do you agree with n plus 1? Okay. So 2 to the power of n for group by cube and n plus 1 for group by rollup. Who understands the difference between group by cube and group by rollup? Okay. Not maybe everybody. So look at it again offline. Again, the difference of pattern is that the group by rollup has really a wave going from the right to the left. Group by cube is more symmetric. It's the entire power set. All right. And again, group by rollup is used when you have a hierarchy in the same dimension and you want to compute the intermediate subtotals. Group by cube is when you have multiple dimensions that you want to do it with. Okay. So this is what you can do with SQL. You can do much more than that, but I wanted to give you a few examples. And the new thing really that I wanted you to think about is, in that case, SQL is the physical implementation. It's the physical language of something of an even higher level that are the cubes with slicing, dicing, roll up, drill down, and so on. It's a completely different world, but you can implement it on top of the relational world, which becomes the physical layer. Now, what about a language for actually manipulating cubes that makes it easy? That's MDX. So just so that you see a little bit what it looks like, but it's not part of the material to actually know that language. That answers the question you asked earlier. How does MDX deal with that, with hierarchies? It uses the dots like this, right? So you can navigate inside a hierarchy like this. SQL cannot dice. MDX can dice. And the way you do that is that in the select clause, you can say on columns and on rows, and that tells the system this goes on the columns, this goes on the rows. So this is used for dicing, and the slicing uses a where clause. And you see again my hierarchy, right? I have a hierarchy of products in that case, and I just use the dots. You probably noticed, of course, it's only a syntactic detail, but in MDX, they love these angle brackets in there. This is just the syntax they use instead of the quotes. So that's kind of the flavor of MDX. All right. Again, you don't need to learn it. You just need to know that it exists. So there is a language that is native to data cubes, that supports the dicing, that supports the dimensional hierarchies, and so on and so on. Right. So this is implemented in some of the data warehousing systems. Okay. So by now, you realize that SQL is a language for tables, JSONic is a language for trees, MDX is a language for cubes, Cypher is a language for graphs. I hope that the pieces of the puzzle start making sense now, right? We have different data shapes, different data models. The high-level principles are the same. You have query languages tailor-made for the model. You have physical implementations that can be different because of data independence. You can implement it in many different ways. And so on and so on. To complete that picture, I need to show you syntax as well. So we have syntax for tables, that's CSV, for example. We have syntax for trees, that's JSON and XML, YAML. We have syntax for graphs. I showed you Turtle and some others. There is also a syntax for cubes. In fact, there's also several syntaxes for cubes. I'm going to only show you one of these syntaxes. That syntax is in fact called XBRL. Who heard of XBRL? Not sure if it's known to the general public. Okay. So XBRL means Extensible Business Reporting Language. It has been used since now more than 15 years by many governments around the world in order to ask the public companies to file their reports in an electronic machine-readable format. So in the US, for example, there are 10,000 companies who have the obligation every quarter, they have to create something in the XBRL syntax for their reports, the balance sheets, the income statements, the cash flow statements, and the SEC mandates them. So it's submitted via a system called EDGAR. And the benefit of that system, because there's many benefits, one of the benefits of this is that now when there is an issue with a report, something is not valid or a bit strange, it can be rejected immediately by the system. The company tries to file, immediately they get an error saying, no, you need to fix that. Before the electronic format, it could take weeks until a human being saw the mistakes and had to correct. So this is has to correct. This is an improvement over what was before. So this is just an example of here. It's a fancy view where we have a hierarchy on the rows. So you see it's an accounting use case. And then we have a dimension on the columns, which in that case is the time. This is Europe. This is the European Union, the European Securities and Markets Authorities, the equivalent of the SEC. And they have also asked, I think now it's been 2 years that they ask companies to also use XBRL for their filings, right? Now, it turns out that the syntax was originally XML. So this is why, you should not underestimate XML. It's really used at a lot of places. So all of what you've learned in XML, XML schema, and so on, in fact, it's used in XBRL. This is an example of a company that filed some profit loss. For example, you see it here, that's the measure with a unit and a specific context somewhere else. And here, there is the number in there. This is all inlined in an HTML document. You can go, if you want, go to the company's website, right? Go to a European company website, go to investors relations, you can find these reports. Fancy looking HTML documents, and if you look inside, you will see these data cubes. All of the numbers here tagged with the coordinates within the data cube. And the context, just to show you, basically, so this is the European version, this is the American version when it started 10 years ago, where you again see XML. So these are the assets, these are the numbers here, and again, a reference to a unit, US dollars, and this is the precision of the number, meaning that the 6 zeros here are not very important. But again, this is one cell, one little cube of the gigantic data cube. And these are, if you follow these foreign keys in there in XML, you will reach here some context with that's called the central index key. It's the way that in America, in the US, they index the companies. So this is 21344, that's Coca-Cola. Here you have an instant period, follows the date format ISO 8601 that we saw in XML schema. Dollars is another ISO, that's 4217. You don't need to remember that. That's just the standard for the currency codes and so on, right? So you see this is all encoded in the syntax, but these are in fact data cubes. And there are schemas and so on, what we call link bases. It's out of scope of the lecture, but it's also XML, right? And then you can define some taxonomy defining what you want to have in the report. I'm skipping that. There's also hierarchies in there. I'm skipping that. You don't need to bother about that. But just to show you that in the case of the SEC in the US, they have created a central website where you can see all the reports. So the system where they file is called EDGAR. And they have these views that are called interactive data. They need a fancy name for this. So it's called interactive data. And you can actually view the data like this in these cross-tabulated views. And you can see here the hierarchy on the row. Here the columns have a flat hierarchy, but this is what it's used for. Now it's used in the US, in the European Union, the Liechtenstein also did it. Switzerland is joining also with sustainability reporting, greenhouse gas emissions in XBRL also. Australia, China, India, and so on and so on and so on. So many countries in the world are now using that format. And that's actually it. So this is what I wanted to show you. So this is a real life thing that uses data cubes for financial reports and sustainability reports. I have 5 minutes left. Do we have any questions on cubes? Who feels like they understood today? Okay, most of you. Very good. So I kept it a bit on a higher level because, again, I just wanted to show you last week the graphs, this week the cubes. Yes, go ahead. Yes, that's exactly what it is. This here is what SQL goes that far. SQL can give you that, a table with the numbers. And then with additional software, you can put these numbers in here. You can display them in that fancy view. MDX can do it directly. MDX, you could generate a query that looks a bit different, but it would be able to directly give you this, right? So this is really just a physical implementation of a part of the machinery that is used to generate that cross-stability view. Yes?
Is there any difference between what the NUX select row versus on, or is that just like a visualization step?
It's only a visualization. It's only a visualization. You would have L shapes on the columns and so on. The data is the same. It's really just some symmetry axis on the diagonal. Yeah. Mm-hmm. Any other questions? Yes? So in the SEC has the website. In Europe, I think the current regulation says the companies have the obligation to put them on their website. So it's on the website of every company. But the European Union is now currently working on a new portal that would centralize all the data. And now as data analysts, especially the data science students among you, you can actually go ahead, take that data and analyze it. So that's actually the goal of all of that, to have publicly available data. Okay?
There's a question.
Yes, I'll finish with that question, then I'll let you go. I see you were starting to...
I took a look at this week's quizzes. Many concepts terms are not discussed in lectures. I'm wondering, would we expect this for the exam? Knowing things that are not discussed in lectures.
Can you write to the Moodle forum? Then I'll tell you about that. By the way, next week, so tomorrow there's a guest lecture. Please come, it's going to be Oracle. Next week, I'll talk about the exam, more details about the exam, what's included, what to expect on the computers. And then we'll celebrate the end of the semester with a quiz. You will play against the TA. If you know Icegagger 100 on TV, that's pretty much what we are going to do, just to celebrate the end of the semester and the holidays. Right? So I'll come back to you on the question. Please send an email or Moodle and I will get back to you. Thank you very much. Have a great evening.